All right, hi everyone. So welcome back to another installment of AI BDS 2. So today it's online. Why? Because whenever we have something that is really important for exam preparation, I like to do it online so you can rewatch it. This is why we are recording it. The next two appointments, of course, will be in person, also the exam preparation. But I feel when we're going deep into some calculation, these were also some comments from the previous semesters. It would help if we could like rewatch it, right? So since and also I have improved the amount of calculation that I actually show, and not just like overwhelm you with it in the exam. So don't worry about it. We will go through all these things. So last time, what we did was we talked about LSTM. We actually finished LSTM almost. Um, and so today we're gonna round up LSTM and a little bit of CNN. We try to also get like a nice frame, compare them. I also told you it's very important to know what are hyperparameters and what are parameters. So people get this confused, and I really want to make sure you understand this because this is true for all the deep learning things, like for ANN, LSTM, CNN, like basically all of these can be thought of as a new artificial neural network, right? Just that the layers are somewhat different and that they function somewhat different, and that they might be put together different. But we will see at the end that you, for example, could also, if you want, you can put a CNN on top of an LSTM if you want. Like uh there's no one saying you can't do that. Like you have to make sure it makes sense and the inputs align to the output of the one aligns with the input of the other, but there is nothing that prevents you from putting them together, right? Even so, in things like PyTorch, so the Python implementation, you can just add, as you can see, and as you saw last time when we spoke, we had this, we used these things here, like in PyTorch, you define an LSTM like a layer, neural network dot LSTM. So this is an LSTM layer. I just define it, right? Or an LSTM with number of layers too. And then I have a certain input that it requires. Like I have this input vector, and it requires exactly that kind of dimension. Like the input vector, I know how many time series in parallel, how many time steps, so how many t, right? And of course, how many how many information I give in one time step, right? And then the LSTM also has an output. Like this is sometimes called the hidden output. This is actually our HT, so this is our short-term memory, which has the same dimension as our long-term memory CT, right? So it's the same dimension for HT and CT, like you can see here. We already spoke about this, and now nothing prevents you from just putting a CNN either before or after, right? Um, and also nothing prevents you from saying, hey, at the end of the LSTM, so here, right here. So I have these layers and I have all these times. So we have here, we have this structure basically. So this is a nice image of the structure an LSTM actually could look like, right? So you have the time. This is the time window, right? So this is like the number of times you go through it, then the number of layers. And what you could do at the end, like for example, you want to say, hey, I want to classify a process, right? And the process is made of a lot of data. Like here you have the raw data, maybe some sensor data here, and then you have some other more deeper data, right? And then in the end, right here at time t, you want to use this to classify the whole process, right? You could just put in a normal neural network here, classification neural network, right? So you're gonna take this output, right, from the LSTM out, which is actually the age at, this is a large T, at time T, so at the last thing. So this is the output. We know HT is the output vector of an LSTM. And this is the last cell, so to say. So the cell at time T. So this is the input, and then so this is the input size. For example, here its output size 256. So I have 256 neurons, bop, bop, bop. So I have one input neuron, bop, 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 256 input neurons, and then I just do a fully connected layer, right? And then I have a classification maybe, right? So an easy one could be if this is an okay process or not okay process, or I could have whatever I like. Like I can have classes, like risk classes, how risky is this process or whatever, right? I can also do this like basically I can put this network also at the end of each time step, right? I mean, it's my choice, right? Whatever I like to do. I mean, it's simply my choice. It's easier to do it like that because as you see here, I can then define an LSTM with the hidden layers and with the sizes, and then I can just take the output of the last one and just put it into a network, which we would usually do. But we could also like do separate LSTM layers, right? And do it like that, right? So we can use this because we don't have the number. We don't have the number. This is just the input number, right? So we could, for every output, we can also define like another network that calculates, that takes the output and calculates it, right? So I just put it into the LSTM as a part of it. I put in a layer, so I can just layer it, right? So just so you know that we can be very creative here, right? So while we focused on different model classes, and it's easier for you to understand because these are the building blocks. I don't want you to think of these as this is like a method I will use now, right? So this is like I use this method from front to back and nothing ever will change. Like this is what we usually do, right? So usually when you have a time series problem, because LSTM is a mighty tool. Like, for example, you are not restricted to having one output. You can see here, we have two outputs here, right? We can have 256 outputs, right? It doesn't matter. You can configure the LSTM however you like. You can say, okay, I want an input of 100 and I want to put out 200. I want an input of 200 and I want to put out one. No one cares. Like you can do whatever you like, right? Doesn't have to work, but theoretically, this is a very mighty tool, okay? If you have enough data and if the patterns are there, you will be very successful using this. It has some disadvantages when you go really big, right? And with big, I mean specifically big in the form of the depth, right? So it's limited in its depth, specifically not because of the LSTM layers, like there's only so much you can get from time, but because of the number of time steps. We will talk about this when we talk about transformer models, right? Next. However, it's a very mighty tool, and so I want to emphasize this. And I also want you to think of these as tools and building blocks at the same time. Like you can only use an LSTM and get a result, no problem. But you can also use, like we learned that an CNN can extract things from images. Now, what if you have like images over time? Like you have an image at t equals 1 and you have an image at t equals t, right? Might be cool that you have a CNN that extracts cool features and then just use these features that it extracts, so the last layer, as an input for an LSTM. So this might be your xt value, your xt equals 1, right? Vector now. And the same here, extracts and xt or xt equals t value, right? And put an LSTM cell here. Like you can do this, right? I mean, you have to think about a lot of things. Like it's not that easy as I draw it, okay? From a programmer's perspective. However, if you're not that bad and if you can think of how to transform the input and output, because this is all that matters, right? So getting to know what I have to give into this model, I have to put into this model, and then as far as I can see, I just have to get this x vector, right? So I can have like batches of time series at one time. I can have how many time steps do I want. So this doesn't really change, right? So I have like 40 pictures here. I have 40 time steps, right? It's not a problem basically to use this, right? So if you think about it, this is probably a nice way of building a network that can have pictures over time, which we sometimes call movies or videos, right? So if you have like video data, this might be a way to go because video is nothing more than pictures over time, right? Obviously, right? Okay, yeah, sorry, I have to little espresso here. I don't know how you're feeling. I'm just like melting in my office right now. So if I melt like the Indiana Jones guy, I'm very sorry, right? Um, but I hope it won't happen. Okay, so something I want to add. Like last time we had this on the Blackboard, and I asked you, hey, what's the dimension of CT? What's the dimension of HTN? We said we can basically vary this dimension, and I just explained, right? So the dimension of HT is the same as CT, and why is this? Again, some student cleverly said, okay, it has to be because we have to multiply here, right? So we have to, they come from the bottom and we have to multiply them and they need to have the same. Otherwise, if they don't have the same size, we cannot multiply them, which is totally correct. Like, see this here. Okay, now I want you to look at the building, at how this LSTM is built, right? So, and I love this graphic for it. What do I want to achieve with it? Well, now we want to actually know how many parameters are in an LSTM. This is actually what interests us right now. And this will also help us to answer I think it's the last question in the mock exam. So in case you haven't realized it yet, I uploaded a preparation exam. And the last question is the most difficult one of the exam. Difficult. It's the one where you need to calculate the most advanced stuff, or think a lot. And so we want to work towards answering this kind of question. So, and what we're kind of missing is the number of how we determine the number of parameters in an LSTM. And this one for me is even simpler than a CNN. Like we talked about the CNN, we had this whole table and I talked you through it. However, in an LSTM, it's pretty easy, right? Because an LSTM is nothing new. In an LSTM, we actually just have 4 neural networks. That's it. We have 4 ANNs. So we just calculate the parameters of these 4 ANNs and we add them up. That is all we do. It's super easy. And if this isn't easy enough, all of these ANNs have the same number of parameters. So we just multiply them. We calculate it for 1 and then multiply it by 4. Right? So the only thing that changes here is here that we have in the candidate layer, we have the 10H function, but it's just a function. It doesn't change the dimension, just another function applied. Okay. So let's have a look at this neural network. So this is called a dense layer. So we also call this fully connected. So this is a fully connected ANN. And these are all fully connected ANNs, and I have 4 of them. Very important. Please pay attention because sometimes it gets confused. You see these here, right? These 2 things. So in this layer, like in the output gate, what happens? Okay, really important. In the output gate, as we spoke, we determine, as it says, the output of this LSTM cell. So this is our new short-term memory that we put out. And this is obviously determined by the long-term memory. Until then, we just change. You can see here, we change the long-term memory. So here we forget, and here we add to the long-term memory. And now we actually use the long-term memory to generate the new short-term memory, which makes total sense. And sometimes people are confused because there is a 10H here, right? So this one is a 10H function. But it's just applied to this vector. So it's just a function applied. This is not a neural network. It's just applied to these 2 blue thingies here, right? It's just applied to these 2 thingies. So if they are 10 and 20, this is now 10H10 and 10H20. It's just the function applied. This is not a neural network, okay? So there are no learnable parameters here, right? This is the only thing where I feel like people get confused. This is also not an activation function in this case. It's just a function applied, right? To build a candidate that has that is between -1 and 1. It just makes sense since we cannot have like unlimited or very large numbers. This is all it does, right? It's just for the math. And as we said, when we want to produce candidates like here, we use 10H because it needs to be able to be negative, so go into the opposite direction, or strengthen it with plus, right? So when we add to the memory, we also want that we can actually subtract. Like this is not forget, it's not a multiplication, but we can go into another direction, right? So this is just all it is, right? And of course, the memory usually has a lot of values. So here it has 2 values, and we also change them, right? So this can be negative, this can also be positive, right? So it doesn't matter. Like we multiply everything by a vector of 2. Okay, so very important, this is just a function that is applied. This is not a neural network. So we only have 4 neural networks. We have for get gate, 2 in the input gates and 1 in the output gate. So 1 for get gate, 2 in the input gate. So this is sometimes called like the input gate. This is sometimes called the candidate layer in the input gate. So but you can summarize them as input gates. So if I ask you about the gates, it's enough if you write for get gate, input gate, output gate, right? This is enough. But you can denote that the input gate has 2 neural networks, one that waits the addition and one that produces the addition to the long-term memory, to our cell state. All right, so 4 neural networks, and then we just calculate. That's it, we just calculate, right? We just do exactly the same thing as we would if we calculate a neural network, right? So basically, this is fully connected, right? This is fully connected. So let's see. Fully connected, and let's write it down. So let's write it down in the way that we actually know this, right? So we have 1, 2, 3, 4, 5. So this is, I just drew this, right? And then we have 1, 2, right? And don't forget the bias, right? This is the only thing you could miss here. We have a bias. We have a bias, right? And now we just have weights, right? And this is it. We just have weights. Like we have one weight to this and one weight to this, right? So sorry, this is sorry, one weight to this. I'm sorry. It's very hot. Okay, so basically what we do is we multiply the number of input neurons, right? So this is like the number of input neurons. So we have basically, it's, if I formalize it real hard, right? We have a dim of ht, right? This is ht minus 1 here, but it's the same, so it doesn't change, dim ht, right? We have dim ht plus, I'm gonna make it plus the dimension of our input xt, right? So this is 3, this is 2, plus 1, because we have a bias, right? Don't forget the bias unit. We have a bias unit, and that's it, right? So, and we have a bias unit, and then we multiply this by how many outputs we have, right? Because each element here is connected to all the outputs. That's it, right? So each element here is connected to all the outputs. So each element has 2 connections, right? So this is multiplied by dim of ht, or if you will, in this case, dim ct, right? So it's the same. Dim ht and dim ct is the same. So if you like it better, you could write ct because this here changes ct, but it's better to write ht because it's the same. So knowing that dim of ht is the same as dim ct. This is important so that you can actually write ct here. So just need one value. Okay. And now calculate this for our example, right? We calculate this for our example. So let's see. Dim ht 2. 2. Dim xt, sorry, dim xt is what? Is 3, right? And plus 1, right? Plus 1 times dimension of ht is 2. Okay, so calculate this. This is, let's see this. This is 6, right? So we look at this. This is 2 plus 3 plus 1. And we multiply this by the number of outputs, and we get 5 plus 1, 6 times 2. Sorry, 6 times 2 is 12. Right? Okay, that's it. So we have 6 times 2 is 12, if I'm correct. So you have to stop me if I'm making easy math mistakes, because it's like 100 degrees in here. So this is 12. Okay, so we have the numbers for one network. And then we always multiply this whole thing here by 4. That's it. Because we have 4 neural networks. This number doesn't change. It's always 4. If you have it for an LSTM, LSTM structure doesn't change. This is a set. LSTM cells always like this, right? There is no way that this number changes. Like if you do something, some custom shit, okay, but you have to write your own network structure, like your basic numeric vector thing. Like if you use an LSTM as we talked about it, and if you use an LSTM function like this, it's always the same, right? It always looks like this. It has, forget input and output gates, it has 4. So we multiply this by 4. So 4 times, which equals 12 times 4, which is 48. So we have 48 learnable parameters here, right? And now you would ask, okay, Kai, very nice. Okay, who gives a fuck? Okay, but how does it change over time? Does it change over time? That's the big question. So here we have 40 time steps, right? So it means we have 40 cells. We have 40 of these cells, right? Does it change? It doesn't. Same parameters. Otherwise, it wouldn't make any sense. We keep the dynamic, like it cannot change for every cell, every time step. And why? Because the number of time steps right here, number of time steps is not a parameter of the LSTM. This is also not a hyperparameter. It just comes from the data. And this is a very special thing you have to know, right? It comes from the data. Like it just says, hey, I'm going to provide the data in that way. Like I'm going to provide a data that has 32 time series. So for example, 32 sensors, 32 temperature sensors, or it could also be like a batch at a time, like you can feed them the time series at once because it's always paired, right? This is always paired. Like it doesn't have to be different sensors. It can also be just different sentences, right? So it could be multiple of the same structure. Like for example, if you want to that the network puts out wants to get this input, like you can do it. There is no way because it puts out 256 values no matter what, right? So basically mapping this input to that output, right? This is what you want to do. And if it makes sense, you can do it. Like here, you can, for example, have like 32 sentences, like sentence 1, like dog goes, sentence 2, the cat goes, and whatever, right? Then you want to predict the next thing. So you can do this, right? There is no one stopping you. So this is the general dimension. Now, if you have like a classical time series where you have like one time series where it just goes like a stock market, that this will be 1, right? Obviously, because you just have this one stream of data, right? So in a classical time series, this will be 1. But no matter what, this is why I said this is a very mighty tool where you can have multiple time series put in at a time. However, as you can see here, this is not part of the actual network structure, right? Because it just says it just parallel. So you put in the first sentence, and the sentence is given by xt, right? So you have x, you give an xt, you give an xt1, and then you have a different cell that then you put it again into another cell that is actually the same cell, but you do it in parallel, right? So this is true parallel, right? And this is basically it. So it's very, if you're confused about this whole input thingy, just remember in the classical setting that we usually have, right? You can act as this is 1. So we have 1 with basically 1 value, like a stock market value, right? So this is a stock price, and this is T. And we have multiple T, so we look. So we have 40, this is like 40 T, this is exactly this, right? And this is the dimension of the input that we have. And this is usually would also be 1, right? So we just have like this one value at a time. One value at a time, right? This means that we have 128 values at each of the 40 time steps, right? This is the input dimension, right? And in parallel, we have 32 time series in general, right? So that's it basically, right? So it could be that here, this is like not given. This is like this input is not just given by one variable, but there are two variables, like, right? And this is what it actually could be. So it could also be that the sensors are here, right? So we have 128 sensor readings at the time at one of these 40 times. And then again, we have 32 situations. It might be better to call them situations where we have them, right? So this might be another day or something, right? So if we have 40 for each day, then this might be another day, could be another batch, right? And this is how we do it. Okay. So, and BTF, this is the thing. Okay, but it won't be that detailed in the Excel. But it's always good that you understand how the cell is built, and of course that you know, hey, we can actually have also other layers. Like this is one LSTM cell here. So this here, this is that, right? Each of these things is one of this. Like we have a cell. This is at one time step only. So this is also here, basically. So this is one cell. This is one cell. This is one cell. So as we said, this cell then gives its HT0 is then the input of the next cell. Not the next cell at T equals 2, but this cell, right? At the next layer, right? So this is all at the same time. So this here is basically a zoom of this here, right? If you want, like how they communicate, okay? So, and like you see that it can become very complex. However, if you think of it, if you use this one right here and just say, hey, I can put in more of these here, right? We always have to draw them. And I can put more of these here, and then I just can calculate, right? And then this will always hold. Like just calculate normal neural network like we've learned it in the beginning, how you calculate the parameters in a neural network, right? So this is all. This is basically all. And it's very simple. You just multiply them, just multiply this with that because it's fully connected. So we have connections from this to each element here. Like, okay. And you can practice this. So I suggest you practice it and see, hey, what happens if I put in this red? So for example, you could just calculate what I drew now, right? So instead of 3 here, we have 5. Instead of 2, we have 3. We have always one bias, so this stays. Remember, you have to correct this also because we have now 3 here. So this would be 3, and then you can calculate it, and times 4. It's very easy. It's always the same, right? And these are the numbers of parameters in an LSTM. All right. Okay. Perfect. And one more thing I want to mention because of the preparation thing. Some of these are the only capacities, the only properties of the network that go into the parameter calculation, right? Because it's just how many parameters do we have in the cell. Why is this important? Okay, because this is just what it is, right? This is for each cell, okay? So we have 4 cells. So this is one LSTM cell, right? This is one LSTM cell, like one cell, right? And each cell has the same, except if you have more layers, right? So this is for layer 1, right? For layer 2, you have to look at how the cells are designed there. Now in layer 2, we know that the output is the input of the previous layer, right? So if I'm very tricky, I give you a task like this where I give you L1 and I give you some characteristics of the second layer, so of this one, right? Oh, this is layer 0, this is layer 1. Sorry, to keep the same. Then I give you some characteristics, but you know that the input of layer 1 will be the output of layer 0. So if I have 3 here, then the input of then the X input of layer 1 needs to be free. This doesn't, but I have to give you the HT because you can design it. This is something you decide. This is an architectural hyperparameter. You decide how many outputs you have. What do you want to memorize in the short term, right? And then again, the rest will calculate itself here, right? The input is set in the subsequent layer. It's defined by how I decide the data in the first layer, obviously, but I will obviously give it to you, right? Obviously, this is the input dimension, like xt, the dimension of xt. I might be someone who says, okay, we're gonna use some fancy words, like we're gonna use an embedding layer of dimension, an embedding layer of size 300. And you will know what that means when we talked about transformer models. And then you will see that you can also use embeddings as input for LSTMs, by the way. However, this is nothing that we discuss now. And so basically, this is just how many inputs to have, right? And the subsequent layer also has these inputs, and this increases the number of parameters as a whole. But I will then express the question like I expressed the question actually in the last question, the preparation exam is exactly such a question. We will talk about this in exam preparation. So you have some time with your knowledge today to calculate this. And yeah, so it's a little cheeky, this task, but I thought this time I put some more difficult tasks in the preparation exam to actually, and then maybe put some easier tasks in the real exam, not the other way around like I did in the last times. Okay, so, but we will see about it. So very important, calculating the number of parameters in the LSTM. Why I am so keen on calculating parameters, you think? Because it gives us a sense. It gives us a sense of how long the training will take, how complex the network is, the parameters, right? So we had this in CNN, we will have this in LSTM, and we will have this in transformers and GPT models, which will be exploding, right? The parameters will be exploding. So the number of parameters will be rather large. Okay, so what I want to do now, I want to go from LSTM to an overview. Like we have so many like parameters, hyperparameters, and I want to sort it out for you. Like I want to go through and repeat it. So this means we're gonna go back to CNN a little bit, and then we're gonna go to LSTM, and then we're gonna start explaining transformer models based on the LSTM architecture and see some caveats that we have with the LSTM architecture. But as I said, I'm a little bit more interested, maybe that I was last time, in you having actually the ability to understand it more. So we're gonna have this thing called exam prep here, and you see I have a lot of things here, and I will briefly talk about some of these things, but some of these things are optional. Okay, so I'm gonna enlarge it, of course, for you, so don't worry. This is too large. Okay, so I also uploaded this. I think I uploaded this. This is the full one. Yeah. So you can see this one is like a cheat sheet, and I don't worry that you see ChatGPT tables. Of course, I used ChatGPT, but I corrected it. There were some things wrong, right? So be careful when you use it, right? So the best results, this is when you have knowledge and then use it, right? But I just used it as a summary of things. So, okay. Now, one important thing I want to mention, when we have hyperparameters, oh my God, it's even, wait. Oh my God, sorry. The first thing you should have the correct spelling. This is the first thing you should have. Okay, I'm sorry. Is that we differentiate between hyperparameters and parameters. So there is another concept that is not really something that is named in the literature. Like hyperparameters are really like small screws, like values, like the learning rate, you all know, where I can set a value basically, right? I set a value and I configure the behavior of the model training or of the or how the model behaves and so on. And this will influence model training or inference and so on. So and how the model performs in general. And then there are parameters, and parameters are learned. If you don't understand the difference between those two, you are absolutely screwed. Like this is a must know. Like hyperparameters, if you like a repetition, hyperparameters, we choose. We choose them. And parameters are trained, right? They are the result of the training through machine learning. Like we don't have to take care of those. Okay? So, and now what I want to do now is what we have here. First of all, we're going to talk about the hyperparameters, right? We're going to talk about the hyperparameters that we have. We have talked about the parameters, so you should know what the parameters of CNN of a CNN is. And the hyperparameters are more complex. And for the hyperparameters, as I said, there is a category that I cannot really put my finger on how to name it, right? So I've called it architectural choice, right? An architectural choice means it's kind of for me, it's actually is a hyperparameter because you said it. Like I like to easy logics that people can understand. So you choose it, right? Means that you decided. And whenever you decided, it's a hyperparameter. So something that is not learned. And something that is not learned is also concerning architectural. So you can basically divide the hyperparameters into like architectural choices and real hyperparameters. So basically screws, numbers, so non-architectural choices. Like an architectural choice in an ANN, right? So you can have this and this. And in an ANN, this would be, for example, an architectural, this would be in an ANN, this would be the learning rate, right? In its standard ANN, this would be learning rate. And architectural choice would be number of hidden layers, for example, in ANN, right? Number of hidden layers in ANN. So in standard ANN, right? Okay. So this is basically like a number you could tweak, you can optimize, and this is like how the picture looks if you draw the picture of the network, right? Okay, cool. Let's go on. So this is kind of what I differentiate. So you can see this column right here. Like this is the architectural choice. You can see this column kind of denotes that. And in LSTM, there are some debatable differences. So it's not really necessary for you to differentiate it, right? But I want you to know that for me, there's a bit of a difference between having a hyperparameter like learning rate and an architectural choice. But they are both hyperparameters in the sense that we choose them, right? So they are not like neither externally given nor are they trained. Okay, so and of course I have packed these tables. I've also deleted some things that were wrong. I've packed these things to the brim. And what you see is, and this is very important, red thingies are optional and not relevant for the exam. Like I will not ask you about these in the exam, right? So, and you don't have to calculate or give this, but I included them as a thing of information, right? But they are optional. And I also prepared an optional sheet for you where you can read about them. I feel I have to inform you, but I also feel like we have already learned quite a bit. So I don't want to, the things you have to remember for the exam, since you can only use notes, it just would mean you have to print more and so on. And I'm pretty sure each one of you will read the PDF and will understand what they are. And they are not complex things. Like they are very easy things to understand. So don't worry about it. Okay, let's go through them. Okay, we're gonna start with the CNN. So we're gonna go back to the CNN now, right? This helps your brain go back a little bit and say, hey, what was a CNN again? What were kind of, and we have like the layer component here. So remember in a CNN, we had an image input. And the first thing we had is a convolutional layer that basically scanned the image and put out a number of features, right? A number of feature maps. Okay, so here we have some architectural choices, and we're going to start with that. We have a number of convolutional layers. So these are the number of filters, right? Number of convolutional layers. So, sorry, the number of convolutional layers in the network. So this is like in the whole CNN. In the whole CNN. So this is basically how many layers do I have? Like I have a convolutional layer, right? I'm gonna have this as a package here with all the things like with pooling and ReLU, right? So this is a package, and how many of these do I have, right? So how many of these do I have? Then it comes the same again, then the same again, and I just count how many of these do I have, right? Until I have the fully connected layer. Okay? This is the first hyperparameter. Then I have the number of filters per layer. Like in this layer, in the first convolutional layer, how many filters do I have, right? So how many filter matrices do I have? So basically, how many things do I scan, right? So we also call this, I think we also call this D. So this is like D0 was the input, so this was the channels, and the subsequent D were just the depth of the layers. Okay, so then the kernel filter size. So what's the kernel size, right? So what's the size of these things? Like, is it 3 times 3? So this is the size. So we go from biggest architectural challenge, very meta, and get smaller. Okay. So, and now we see that these are architectural choices, and the kernel filter size is a classical hyperparameter of the convolutional layer, right? So stride also, we know how fast we move. Basically, do we move 1 pixel and so on? And do we have zero padding? Do we put zeros around it? And then there's also something called dilation, right? Dilation is if we poke holes into the filter, right? So, like a good cook, I have prepared something for you. This is optional, right? I actually thought I have had it all. Let me see. Didn't I? Yeah, okay. I have a whole. These are all optional mechanics. Okay, so these are optional layers, right? Just zoom in a little bit. And just shortly, I want to explain it. This is optional, right? But please still listen. So it's pretty simple. Like, this is a normal filter. What you see on the left is a normal 3x3 filter, right? Easy. We know how it works. We put this over the image and move it by stride, okay? And if we choose a large stride, we get a smaller feature map in the end because we skip a lot, right? Now, another thing of doing this is we can just have a filter that skips tiles or pixels, right? So here we skip every second pixel. Here we skip 2. We have 1 pixel and skip 2, right? So that means that essentially our filter size gets larger, but we have the same number of parameters because you see the blue thingies, these are our parameters, right? So this also repeats what are the parameters in the convolutional layer, right? Yes, these are our filter values. So these here, my red dots here, these are the parameters of the CNN, right? These are parameters of the CNN. Okay. So, but you see, I still have 9 parameters here. I have 9 parameters here. So it doesn't change. The number of learnable parameters doesn't change, but I get a larger image by skipping this because I assume that close together have the same information. So this is called dilution. This is dilation, right? So if you want, you can check it out. I have some example calculations here for you. So if you want, this also helps you to practice. All these elements help you to practice. But quickly, let's go through it. So we have an easy input feature map 5. So this is an input feature map 5 times 5. This could also be an input image if you want, but it's size 5 by 5. And then we have a 3x3 kernel that looks like this. And these are the settings. So we have stride 1, no padding. So this is all you need. And now you can calculate, right? So, and then it says we want to compute the convolution around the middle pixel. So these are all the things I would need to give you in an exam, right? If I want you to calculate one feature map value, right? I could also say calculate the whole feature map, but to be honest, it's a little much, right? So in an exam, because you have like 3 times 3, you have 3 times 3 feature map, which is pretty hard, right? So we don't want that. Okay, so we take this. It's again displayed here. Like we have no dilation. This is just normal, like we said. Okay, so without dilation, what we do is we're going to take this matrix like here. This is our filter. And we just multiply it with this patch. So get dilation. So we have 7 times 1, 8 times 2, and so on. Okay, and so on, and we get minus 40. I actually recalculated this. So very important, if you let ChatGPT calculate, always check, right? So this is indeed minus 40. So we have minus 40 without dilation. Okay. And now we do the same thing with dilation with rate equals 2. If dilation has one hyperparameter and it's called dilation rate, and it just says how many tiles do we skip, right? So if it's 1, we skip nothing. Like R equals, it starts with 1, and this is 1. Like this is, as you can see, this is R equals 1. So don't say it's R equals 0. This is very important. So it starts with 1, and 1 is the basic. 1 is the standard. So this is very important. It doesn't start at 0, and 1 is it skips 1, but it starts at rate 2. So if we have rate larger than 1, so rate 2, it starts actually the actual dilation. Okay, so rate equals 2. With dilation, we skip every. And what I did now is, this is still the exact same input image. And now, what's very important, as opposed to stride, we now actually change what we look at the input, right? So you can see here, I don't change the filter. Like the filter stays. You see this? I don't change the filter at all. This is very important. Like, I don't change the filter is still the same, but the pixel I look at, they change, right? So obviously, like dilation means I multiply the first value, then I multiply with the third value and not the second value, right? So, and so this means that now, what I have here is I'm having this one. I'm having this one. This is very important. This also means that our receptive field, like the field we scan, gets bigger, gets larger, obviously, right? So I don't have a 3x3 field like this anymore. So this was the old field, if you remember. But now I have a 5x5 field. So I cannot even scan this because I have a 5x5 field. So I can only scan basically now the whole thing, right? So, and this is how we do it. So we have the first pixel, then we skip, we have the third, we skip, and so on. And so we get this, right? So we get this, and we multiply this by the same filter, right? And that's it. And we get minus 80, okay? And very important is how the dimensions change, right? So we compare it, like this is ordinary. This is the first thing we calculated. Now, the receptive field size is 3x3, obviously given by hyperparameters. And now the receptive field with dilation, it changes, right? So if you want, this is an easy formula that you can use, right? So this is called the effective size. So if we have an original receptive field of 3x3, so if our filter is 3x3, then now we have basically the size k, now the new size k, it's called k effective. So we can calculate this and say, okay, so we multiply k minus 1 by the dilation factor and add k, and then we have 3 plus 3 minus 1 times 2 minus 1. So it's actually 2 times 1. So we have 3 plus 2. And now it's 5. So it's 5 times 5. This is the new receptive field size. So the very important thing is that the parameters, they don't change, right? So we don't need new parameters to learn, but we get a bigger window to look at, right? And important is also the output, of course, changes, right? So here we have an output of 3x3. What do I mean by output? This is the feature map size, right? So have a look. Let's have a look. You see, this is the original 3x3, right? So I start here, right? I start here with this 3. Then I move stride 1. I go to this. And then I go to this, right? So then I go 1. Then I go 1 below, and so on. So I take this, and then I go 1, and then I take this, right? And that's it. So what I have is my feature map is 3x3. If I do this, if I apply a 3x3 filter or 5x5, my feature map size is 3x3. You can try it out by moving it, or you can calculate it with our formula or whatever, right? So verify it however you like. This is the output grid size. So this is the feature map size. So the feature map size in original is 3 by 3. So we have these values, okay? So, and this value, ladies and gentlemen, in the middle here, this value in the middle is minus 80, right? Minus 40, sorry, minus 40, okay? So this is that value right here. And now here it's not 3 by 3 because now the size has changed. It's 5 by 5, right? And our image is 5 by 5. So how many output values do we have? Only one. We've only one output value. Because what happens if I move this? Like I cannot move it. I have a 5 by 5, and if I put a 5.5 on a 5 by, I cannot move it. There's no way because I have already covered everything, right? And that's it. So I have 5 by 5. So I have one number, and this number is minus 80. So the feature map here looks like this. This is ordinary. And the feature map here is this. And it's minus 80. This is the feature map, is one number. Not really a map, it's point. It's one number. Okay? Cool, cool. So this is dilation. Okay? So dilation. Okay. So this was the convolutional layer. Okay? These were all the things in the convolutional layer. By the way, in the convolutional layer, I also explained to you, so I'm going to use green. So in the convolutional layer, let's see where I can put it. So here the convolutional layer has the parameter. Oh, this is sorry. This is not good. Let me just change colors a bit better. Okay, in the convolutional layer, our parameters, and I hope you know this. This is why I actually didn't write it, but the parameters are the values of the filter, right? Values of the filters. Cool. So these are parameters. These are our, not the only, it's not the only parameters, of course, right? But these are like main parameters, but not the only ones, of course. Okay, pooling. Let's go on. Pooling. So here in pooling, we have the pooling type max average, right? So this is an architectural choice. What kind of pooling layer do I use? Very easy. Then of course I have the pool window size. So this is the just to reset the field I scan, 2 by 2, 3 by 3. And the pool stride, yeah, it often equals the window size. So if I have a 2 by 2, I also have 2, right? I have the stride by 2. So these are some, this is a column like typical values. I wouldn't give a lot on, wouldn't give a lot. It's just that you can see, okay, what are modern CNNs, but you can do totally different. Like it could be, as you can see, this is like here, the number of filters reaches from 60 to 1024. It's not like a common, like there's a lot between it, right? So it doesn't really suit you actually, but I just let them spit out and I just let them in, but I wouldn't give too much. I will not ask you about these things. Like these are rule of thumbs and they are vastly different for different applications. Okay, this is all you need to know. Right? And if I ask you this, you try these are vastly different. And then you say, okay, for smaller problems, obviously smaller and so on. So it needs to make sense for you to have this. Okay, so pool stride. So pooling is done. I think pooling is very easy. Then there is something, right? That has been a little bit on my mind since we talked about CNNs, which is the thing, and I'm gonna switch to another thing right now, which is normalization, right? And yeah, so one thing I want to talk about is how we calculate convolutions. Now in the lecture slides, what I did was I averaged, right? So what we did was we had a convolution. So for example, this is an example task. It could look like this. By the way, shout out to Akib for sending it to me. If you're here, thank you so much. So there was a question from a student, and I think I thought I should address it. right? So thank you so much for sending me. I blatantly stole his picture that he sent to me and calculated it so to show you, right? So what I did in the slides, what I did was I had also a 3x3 thingy, and what I did 3x3 thingy, and then what you get like 9 values, like 1 plus 0 minus 1 and so on. You get like 9 values, and then I divided them by 9 and I got like one value, something like this. Okay. And this then was put onto the feature map, right? And so here 0.77. This was in the slide approximately, right? Okay. Now this here, the division, right? We usually don't do that. This is in a very early stage of CNN. There wasn't like where it wasn't very excessive. We could just do it to keep the number small. Now, what we need to do is keep the number small. Like it's not good if we have like values 5 or 10 or 100 because it will mess up the optimization. Like it will take longer. It takes longer to search something in a larger space, obviously, right? And also if the spaces are vastly different. So this is not cool. So this is definitely one variation. So if you get a task like this, right? So what this is like a choice so that I can make it clear to you in the exam. So for example, the task would look something like this. So this could be an exam task. It says, given the following padded input channels and filter W0, calculate the corresponding value of the feature matrix, right? Or feature map. I would probably say feature map. Sorry, probably say feature map. As you can see, you also need to consider the bias term of B0 equals 1 and then hint no averaging. I will write this down. I will say either you can do averaging or no averaging. Okay? So I will give you the hint on what to do, right? If I give you no hint, you can do whatever you like. Like you can let this be or you can do it, right? This is not wrong. Averaging is not wrong. It will not change anything. It will just make the number smaller, right? So I want you to know that there's nothing wrong with it. It just makes numbers smaller, which we want. But there is another way on doing this, and this is called batch normalization, and this is the way it's done normally. This is why we went from the batch normalization to this. And the way we normally calculate convolutions, and this is the way we calculated it in the CNN explainer. Remember the CNN explainer, right? This where you could like with the espresso where you could predict it. And CNN explainer gives a perfect example of how it's usually done in larger CNN, right? So as I said, this is not wrong. Averaging is not wrong, but usually it is substituted by batch normalization, which we will talk about in a second. But since we're here, let's do a little calculate exercise of convolution. So this is a convolutional layer. I'm going to zoom out a little bit. So we have 3 inputs, right? This could be feature maps or this could be input or whatever. And we are interested in the feature map value, right? We're interested in the feature map value. So we know that there is a feature map somewhere here, and we want this value right here, right? So this is the value that we want. This is the value we're interested in. This is also what's asked for. So the corresponding value of the feature map, right? We actually don't have to know where it is. It's enough when you write it down, but you should also know where it is. But you're not required to draw it. Okay, so we have 3 channels, 3 input channels, and for each input channel, we have our own filter, right? So what we do here, if we have this and the bias term, the same we do in CNN explainer. We take the dot product of these 2 matrices, right? Dot product just means L-wise multiplication and then add the values up. Yeah. Don't confuse this with cross product. Please don't. It's wrong. It's a dot product, right? So we multiply this and add them up. So we get a value here. So let's call it value 1. Then we get a value here, value 2. We get a value 3. And then we have a bias. So and we have value 1 plus value 2 plus value 3 plus the bias. And this is then the value. Okay, let's do it. So this is the first value. So this is the value from filter W00, right? W00. So I've written it out one time. So this is -2. So if I multiply it and sum it up, so 2 times -1, 1 times 1, 1 plus 1 times 1 plus 0, plus 2 times -1 plus 0 plus 0, 0, 0. Okay, because 0 times something is 0. Okay, so I've written it out once. So if -2, 0, and 4. So we're gonna take these values. So we're gonna take these values in a second, and we're gonna add them up, and we add the bias term. Like you see, I add the 1, like the B0. Like I add the bias term, and this is -5, and this is the corresponding value of the feature matrix. Feature map. I'm sorry, I'm not sure why I'm saying feature matrix today. I'm sorry. -5. So what you can do now to practice, and what you should do, first of all, you should thank Akib that he sent me this cool task. And then what you can do is, hey, there are other positions left that you can calculate. So if you want to practice, calculate all the other positions here, right? And check if you're correct, because here you have the answers, right? So you can check at this matrix if you put, so for the first position, you should get 5, right? For the second, 4, and so on, right? So if you start here, for example, and do the same thing, like multiply this with that, this with that, and this with that, add the values up. Don't forget to add the 1. There is a shared bias, so of course it's always the same 1. You should get 5. Okay? And if you're feeling very cool, you can also see that there is another filter. So this is just one filter, right? So this is W0. But we say we have a lot of filters, right? We have a lot of filters. Like we don't only have one filter. So one filter means one neuron. Now you have to know that you have, because we have 3 filters here, they are all looking for basically the same thing, but in different channels, right? So, and then we add them up for this one feature map. So this one feature map is basically for filter W0, right? And then we can have another feature map that looks for something else, filter W1. And so again, I blatantly used Akib's image. And then there's another filter you can apply so that you can practice what happens if I change the filter and keep the input. It's still the same input, but another filter, right? And you also can check with the results. So this is the result from, as you can see here, from filter W1, and this is the result from filter W0. So please, if you need practice, there you go. Okay, so it serves a lot of purposes. So I hope this answers the question why sometimes we average, and usually, I'm gonna say usually we don't, because usually what we do is we're gonna do batch normalization, right? See, batch normalization here, right? And I've also added this, so I have added these optional things like batch normalization, and I want to make it really short, right? So the intuition is pretty great here. Like, imagine you are like the teacher, like a teacher like me gives a lot of quizzes. Like we don't have an exam, but we have several exams, right? And what happens is we have a lot of exams, and sometimes the exams are quite easy, and sometimes the exams are hard. And you know what happens? Like if I grade your exam and everybody is like doing really bad, and I feel like, oh, I might have made the exam too hard, and I orient myself. So I assess the exam based on like an average grade. So what I do is I center it around the mean. So, and this is the same we do here. Like we have a batch that we feed. Remember, a batch is a part of the training data, a mini batch. And we just, after activation, so after activation means after the whole package, like after ReLU, so we have convolutional layer, we have max pooling, we have ReLU. And after this, we do batch normalization. So basically after this, we make the value smaller. That's it. If you remember this, that's okay. But we do this basically in the training. It's important because in training we have batches. Like we don't know the next batch. So if we start with an easy exam, so there's a batch coming in, right? In training, there's a batch coming in, and the batch is an easy exam, so it performs pretty well. Then we will adjust, then the batch normalization will adjust it to to the values of this batch, like to the average of this batch. But then there is another batch and it needs to adjust to this batch, right? And what we do is actually in batch normalization to find good values for this, we actually learn parameters, right? We actually learn parameters so that we can transform a value, right? So we have now a value that comes out here. This is our standard value. So this is our feature matrix, and we have the feature map has values like this is x1 maybe, this is x2, and then we have this value, and then this value is maybe too big or whatever, and then we learn parameters so that we can actually like see if we can actually transform these values a little bit, right? So that we can make them larger, we can add something and so on. So basically this is batch normalization, right? That's it, right? And what it does is we have faster, steadier training, right? This is very important because the numbers are smaller. Like we don't have to search, we are still optimizing. Like we don't have to search in a larger area because we have 500 there and 0.002 there is large difference, right? Large magnitude difference. So this is pretty cool. Also, we have the higher learning rates become usable because we actually have bounded activation. So that means they are all between, we actually do a set transform here. That means that the value have mean 0 and standard deviation of 1. So that means that a learning rate of 0.03 actually does something. Like if I multiply this, like it actually does something. So we can actually use also larger learning rates like this. Because multiplying this by 0.25 is not as hard as multiplying 0.1 like times 500 or something like where we can largely overshoot with larger learning rates, right? Yeah, it adds a bit like regularization. Yeah, it's not regularization though, right? So, but of course, noise, like we essentially boil it down and remove a little bit of noise, right? So a little bit of, but not really yet. So that's not really the task. The task is just to normalize it. So basically, if you want easy explanation, the thing I just explained here, in this example, this basically does the divided by 9 thing, right? But it doesn't divide by 9. It's a little bit more intelligent, okay? It actually normalizes the values, okay? Yeah, and that's it. So, all right, let's go. So normalization done. Normalization done. Cool thing. And activation is the activation. When we talk about activation in CNN, so sometimes we have to learn new words for the same activation. It's just value. That's it, okay? It's just value. We have no hyperparameters here. It's just value, and this is just if we put it in or not, right? So we can use other functions here. So this is just an architectural choice of the activation function, but we usually use value. Okay, regularization, right? We've also not spoken about this. So regularization means how can we avoid overfitting? That's all regularization does, right? So there are two things that we can do here in regularization. So the first is, and this is also explained here. The first that we can do is dropout. This is the big one in CNN. So dropout basically means that we just randomly remove neurons. So basically, we only want the network to function with half a brain still, right? So in intuition, again, think of a study group of maybe, you know what a study group is. You all go in the library, you are 10 people, right? But instead of always being there as 10 people, you randomly remove people. So that means that people that usually like maybe benefit too much from other people actually learn something. And I'm talking about dead neurons. So I'm talking about neurons that just profit from other neurons and actually don't do something themselves. So if you remove people from that group, then everybody knows the topic fairly well. And usually this is done in the fully connected layer. So in the fully connected layer, it randomly removes a portion of the neurons. So you have to set a percentage. 0.5, it removes 50%, for example, right? In training. So that means that the other neurons also have now responsibility. And this will help that the network doesn't react so much to noise. Like if you have a lot of neurons, a lot of weights, it reacts a lot on signals because some neurons are purely there to react to these noise signals. And if you remove some of them randomly, they are randomly removed, then you have a good chance of removing these random influences. And this is why a dropout layer just says, hey, remove 50% of the neurons. That's basically it, right? Yeah. And it prevents it's a mean of prevent overfitting. That's it. So it makes that it can generalize well, right? And so we place it usually after fully connected layers, right? So this is the totally classic style that we use, where we just remember we have the CNN, we have two parts, we have the whole thing with the convolutional layers, and at the end we have a fully connected layer that actually is an ANN, right? And so in the fully connected layer, right, we have these neurons like the hidden layer, the last hidden layer before the output, right? So this is the output. So we have like 10 classes of images like in our CNN explainer. And what we do here is we actually now remove randomly some neurons, right, during training. That's it, okay? So pretty cool. So that's it. That's all you need to know about pop-out. Now, it's important that in training, we have so that there's a probability that each neuron is kept, right? And dropped with the opposite probability. So if there's a probability, it checks, it's a random check, is this kept or not? For example, it's 0.5, it has a 50-50 chance. Like obviously, the lower this is, the more neurons you keep, obviously, right? So in inference, of course, new neurons are dropped, right? But their outputs are scaled by the keep probability, right? So if the output is rather large, right? If the output is rather large and it has a low keep probability, then it goes down, right? And that's it. So this is like to make it more generalizable, right? Okay, so, but again, optional, right? So fully connected, we know this, fully connected. This is just a normal ANN. So we have the design of the fully connected layer. So how many hidden layers do we have? And how many neurons do we have in each layer? So this is a normal ANN, right? And here, of course, we have also parameters, right? So here we have also parameters, right? Parameters. And the parameters are just the weights in the fully connected layer. Like the weights, the normal weights that I have also in an ANN, right? I would also have in an ANN. So parameters, oh my God. Parameters here are just the weights. Like ANN. It is an ANN. It's not like an ANN. It actually is an ANN. So that's it. Yeah. And then there are some training hyperparameters, the learning rate. I mean, I didn't have to mask it, but I want, like this scheduler, batch size, also optimizer. So these are some Python things you can see, and so on. A second thing that you actually should know, but we haven't talked about this in AIBDS1, is another thing of regularization, which is weight decay. Weight decay is just an L2 norm regularization. That just means we add to the cost function, yeah, it's pretty easy. We just add a penalty term to the cost function. It's this penalty term we add to the cost function. That means that parameters, the larger the parameters, the weights are, so these are, this could be anything. Like this could be, these are just the parameters. This could be the weight in the ANN. This could be the filter value. So whatever parameters we're talking about, like WI are the parameters, okay? Could also be the filter kernel values, whatever. So whenever we have a parameter, we just add this. Like we have lambda and multiply it by the sum. And we want to minimize the whole function, the cost function, obviously, right? Want to minimize it. So we add this thing, and the whole thing happens is we kind of need to equalize the penalty with meaningful values from the other part. So if you just do a gradient descent or stochastic gradient descent, so we can also do this the same for gradient descent. So the classical gradient descent, is W, make it in this form, is W minus then the learning rate. We call it alpha. Here they have a different thing. And then the partial derivatives, right? So this is the classical thing without regularization, right? Without regularization L2. So weight decay is just another name for L2 regularization. And now with regularization, we add this term here. We add this term in. If you transform it, so we have the old term here, this is the classic term, and now you have this new term here. So this is the new term. And you see that 1 minus, so the larger this lambda is, the more weight we give to the whole thing here. So the more we want to prevent, more we want to penalize large parameters, the more the weights decay. Decay means because this is a number smaller than 0, smaller than 1, right? It's 1 minus, and the larger this value is, the smaller this number is. And this means the smaller the weights will get. Now, so basically you can think of this, we have a standard. If we don't do anything, the weights just get smaller. The new weights just get smaller. Like if this is 0, we change nothing, the weights just get smaller, 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 smaller. So we basically have to equalize it with this. So weights that have absolutely no place because they react to noise, and noise is not caught in the training process, they will get smaller and smaller and be less relevant. So that means that we have more generalization. So that's just it. This is a normal, in neural networks, we call this weight decay. Instead, we can also use this in linear regression. We could use this in logistic regression. There we call it L2 regularization. It's the same, right? L2 regularization, you just add this term and that's it. Pretty easy. But again, it's not part of the exam. But I want you to have heard this because we hadn't had time to talk about this. Okay, this is the CNN, right? And now it gets easier. Believe it or not, it gets easier in the LSTM. Okay, let me get my parameter thing. Okay, so we have what's called the recurrent core. This is the LSTM cell, right? So we have the number of stacked LSTM layers. So this is like, remember the number of layers that we had. So where is it? LSTM, yeah, here. So the number of layers, just this, 1, 2, 3, the number of layers we have, right? This is exactly that. Okay, cool. So number of stacked layers, again, hidden state dimensionality, this is our output dimension. So this is the dimension of HT, which is the same as CT. We have to decide that, right? This doesn't come from the data, right? So we have to decide this. Okay, then there is a thing bidirectional versus unidirectional. We can also actually look if we can look into the future. So sometimes we can look into the future. And this is sometimes important for what? If we have to fill in the word in between, right? So where Waldo. So it would be good to actually know this one, right? So then we use a bidirectional. That's basically it. I'm not going to go into detail, but this is what it's good for. Then the input handling. So the input handling is just, so we have our things that we have here. This, remember, BTF, right? These things I explained last time, and we find them here. So they call it embedding dimension, projection size. This is just the input size F. So if you think, what the hell is input size F again, right? What is it? Like, what now? It's that. It's the number of circles here, okay? This is the input size. That's it, okay? That's it. That's the input size. And so basically the input size is kind of a choice you make, right? It's an architectural, because you can say, hey, this is my input. Like this is the data I want to put in, right? The same with the sequence length. Like sequence length, obviously, how many LSTM cells do I want, right? So this is the window. So that this is the number of time steps T that we spoke about, right? And then we have also regularization. Basically, we can do the same in LSTM. Like we can actually like we can forget things, right? So we can drop out between LSTM layers. So we can have but we can also have drop out between cells, right? So but it depends on what we want to do. So basically, if we look at LSTM, now we can have drop out here. Like we can, for example, forget about not the input cells, but we can forget about, yeah, we can actually forget about things here. And or with the output, we can forget about some things here. And we could also forget about, wait, where is it? Here. We could also, when we go to this direction, we can also forget about some of the output elements here, right? And so on. So this is like, but we can forget in this direction and we can also forget in this direction, right? This is basically what it says. Like whenever we have some neurons, we can just put them away. Okay, so, but I won't go into great detail about that. This is why I also like regularization. We also have weight decay here. We can do the same. We can always like just regularize it as always. Like we have a cost function of the 4 neural networks and we can just regularize the neural networks. Like we can make them not remember any detail when they forget. When they build the short-term memory, we can also do this, right? There's something called gradient clipping threshold. That means that we don't get the gradient, that the gradient doesn't get too large. Like we've solved with LSTM the vanishing gradient problem, but remember there was also exploding gradient. So gradient clipping means we have like a threshold when we have the gradient, so we don't let it grow. And so we basically clip the gradient at some point. So we said, okay, you cannot go any further. Yeah, and we have the batch size, obviously, like we talked about this. This is the number of parallel time series we can put in. And the important thing here to remember is our BGF. These are the same things that we talked about last time here. Let's see that we have here. So we have our things BGF. All right. And we've also find them right here in our hyperparameter. Okay, superb. And as I said, I've created another separate PDF. This one right here with some of the more important optional things. They are all for CNN because it's easier to remember there. But some of the things like dropout and weight decay can also be applied to LSTMs, of course, because they are fairly general and they also talk about neurons and not so much about CNN. But usually they are explained here for CNN, but you can also, like batch normalization, like dropout, there also can also use them, right? So, and I think this rounds it up pretty well to say, hey, we actually can mix and match a little bit, right? So we have our tools that give us an output, and then we have some tools. So tools that give us our output, convolution networks, of course, is our convolutional layer and the pooling layer and the fully connected layer. But we also have some tools that control the behavior of the network, and they can be applied to pretty much any neural network, right? So we have normalization, regularization, right? So and training, of course. Like we always control the training for literally every network, right? So here the same thing, right? So optimization, this is also training basically. This is also training, right? So optimization is the same as training. So we have the learning rate and so on, right? And of course, the batch size is the size we feed in batches. We feed the training in batches. Okay. So, all right. Cool thing. So we have no more minutes left, but this was very important because this will greatly help you for the exam. It might have confused you also a little bit, but I hope this table will help you to see how you can calculate numbers of parameters, what are parameters and not. And next time, we will talk about transformer models. So we will go from LSTM, right? We will go from our beloved, always click the wrong, sorry, we will go from our beloved LSTM model, and we'll identify some weak points, and we will have a short discussion on So don't worry. This is the old version. I'm not using the old version. This is I used to explain it with this, and it was way too complicated. So we're not using the old version. I have a more compact version, and I uploaded already the first part. And as a preparation, right? And since this is also video on demand, I would urge you, right? Because this is a very complex explanation that I can only scratch the surface in one lecture next time. I would really love for you to watch the video, right? And the video is that. Like, this is the best video I could find to explain with the knowledge we have what a transformer model is, right? How a transformer model, which is the basis of a large language model, functions. And they even use values of GPT-3. So you know approximately what are the parameter sizes and so on. And so these are two videos. So this is the first one, and everything here in the part one until then is basically from the first video. So this is some preparation, and this is the second video. Please watch both videos. Because especially this, the attention mechanism is what makes all the difference. Basically, the transformer model is more or less an LSTM with attention. It's a little bit more complex than this, but the attention mechanism is the core, the absolute core, and basically the invention that fuels ChatGPT, right? So there's no doubt about it. Without attention, there is no ChatGPT ever. No way. Okay? So this is great. This is a great thing, but it's also rather complicated. So watch the videos and I will explain this. So the first part you can also read through. Through my explanations here, I've added some explanations and I will explain it all to you next time. And of course, then we will go through, and it stops at what actually the output is, right? But now only thing left to do is to explain what happens between, I explain how the inputs are built and I explain how the output is built. But the problem is we are missing in between. So we're missing actually how we get this matrix in and how we get these vectors. And this I will explain also. So please prepare for it. So because I need to skip some easier steps, probably. I will tell you about the steps, but I cannot go into great detail. So this is what we will do next lecture. And after that, we will have a lecture dedicated to exam preparation. We might finish this in the first half of the exam preparation. And then do exam preparation, speak about the preparation exam. If you have not, have a look at the preparation exam, do it. Of course, we will in detail explain every solution in the exam preparation, which will be the last lecture. But in case you want to practice, check out the exam. It will help you to prepare for it and to be fit for the exam on the 28th of July, I think is the exam. Okay, with that, we are done. We are exactly on time. I want to thank you so much for joining me today. And if you watch at home, hi. And now it's time for a Q&A session. I'm pretty sure people have at least somewhat of a question. Okay, so thank you so much and see you soon.